All right, let's start with section 12.1, which will cover the three-dimensional coordinate system. So 3 learning objectives this time. We're going to hopefully transition from the traditional 2-dimensional coordinate system, that being x and y, into a 3-dimensional system that'll have x, y, and z. So that 2-dimension system, x and y, is our 2D system, and hopefully transition into a 3D system, which, if we're going alphabetically, will have x, y, and z being that third coordinate. That's our 3D system. Additionally, we'll want to visualize and interpret what these 3-dimensional coordinates look like. So we're going to practice doing some drawing. And then we're going to want to be able to plot those points in 3D as well. So starting with just where do we put the third axis? So sticking with our traditional 2-dimensional x and y axis, x goes horizontal, y goes vertical. If we move to 3D, we'll need to bring in a third system, or a third axis. So we just copy and paste the one that we already had. And the new dimension to go with horizontal and vertical is then we'll also want an axis that comes out of the page and into the page. So in and out will be our new axis. So previously, where we had x and y, we had those two axes were at a 90-degree angle to each other. And we called that perpendicular in 2 dimensions. Now in our 3 dimensions, we're also going to want this third axis to be perpendicular to the other two. But when it's in 3 dimensions, we're going to call that orthogonal instead of perpendicular. But we should hopefully have the same requirements about being at 90-degree angles to each other. So if I can hopefully draw a 90-degree right angle square between this new z-axis and the y-axis, then also between the x-axis and the z-axis. So hopefully you can believe that these squares are at 90-degree angles. And we'll label this new axis z. And again, we'll say that that's at 90 degrees. We'll also say that that's at 90 degrees. And again, we call that orthogonal in 3 dimensions. So that is the sort of natural extension from the 2D plane into the 3D space. But conventionally, we're actually going to slightly relabel some of these axes. So let's copy this new set and paste it again, just so we've got those same pieces there. But we're going to relabel some stuff. I'm also just going to clean this up a little bit, get rid of those 90-degree pieces. And while we're at it, maybe slide that over a little, and I'll change this color so that it all matches. Hopefully we still have that going straight to the origin. Cool, so our conventional method for labeling the axes, rather than keeping the XY plane where it has been traditionally for 2D, is we're going to take the XY plane and lay it flat on the ground and then rotate it 90 degrees. And we're going to rotate it 90 degrees clockwise from above. So you end up with the new x-axis hanging out as the new axis that we just drew. That's now going to be x, so it's coming in and out of the page. The y-axis is now going to be the one that goes left and right, and z will go up and down. So this is our traditional set of x, y, and z. And again, we'll call this conventional. One thing that we will have to be aware of is that it's not going to be good to switch any of these letters around. So if we copy and paste this one more time and give an example of one that isn't going to work for us. Looks like I might also make it just a little bit smaller, since this will be the part that doesn't matter as much. I cannot switch the orientation of these axes. So if I instead just switched two of them and had Y coming out of the page and X moving left and right, this would be no good, because now our positive axes no longer match up the way they used to. So this is going to be bad. We don't want to do that. Switching around just two of the letters is going to come up with a permutation that won't work for us. Again, because as long as we keep either of the first two orientations that we drew, all of the positive axes are oriented in the correct directions. But switching just two of them means that our positive axes won't line up anymore. So this third diagram could work if I labeled X going as positive in the left direction rather than the right direction. But as it currently is labeled, not so hot. So again, the reasons why it's not working out is because of that X and that Y. So conventionally, we're going to keep Z is up and down, Y is left and right, and X is in and out, or out and in, for listing the positive first, since out is going to be the positive direction. So those coordinate axes, we consist now of three axes instead of just two, the X, the Y, and the Z axis. Each of those are perpendicular to each other, or again, orthogonal if we're in 3 space. But if we take any two together, we can still say that they're perpendicular. And these axes meet at a common point called the origin. The origin is basically the same origin that it was in 2D space, or in a 2D plane. Now that we're in 3 space, it's still the origin, it's just where all three axes meet together. So the direction of the z-axis can be determined by the right hand rule, which I'll do my best to describe here because I cannot draw hands. But if you hold your right index finger, your right middle finger, and your right thumb, each at a 90-degree angle to each other, you'll get the sort of correct orientation. If the right index is the x-axis, right middle is the y-axis, then the right thumb would be the z-axis. If that explanation doesn't make sense, or if you're just totally unfamiliar with the right hand rule, I'd suggest Googling it, because I'm sure that there are much better drawings than I could produce here. Let's come on with a few more definitions. So the 3 coordinate axes determine the 3 coordinate planes, that being the xy plane, the yz plane, and the zx plane. Those are each drawn out in the figure on the right. And so you can sort of see that the xy plane is the one that's on the ground. It's that brown one. And it is going to cover, or it contains, the x and the y axis, which is why it's the xy plane. Similarly, the yz plane is sort of the one that's, maybe call it in the back, and it contains the y and the z axes. And then the xz plane or the zx plane, order doesn't particularly matter. That's the one that's up against, I guess, that left wall. And it's going to be the plane that contains both the x and the z axes. So in 2 space, we could split up the coordinate plane into 4 quadrants. But in 3 space, that'll split into 8 octants. Since now there are 8 of them, since if there are 3 axes, 2 to the third is 8. And the octant determined by all 3 positive axes will be called the first octant. So similar to the first quadrant, which is the positive x and the positive y axis, the first octant will be the positive x, the positive y, and the positive z axis. So if we sort of see this blue box that's sketched out, that is listed in the first octant. I'll highlight first octant in blue, as we can see that over that diagram, that blue box is in the first octant. All right, and now let's talk about plotting points. So points in 2 space were determined by an ordered pair. Now points in 3 space will be determined by an ordered triple. So now it's x, y, z instead of just x, y. And for example, if P is the point 1, 2, 3, then 1 is the x coordinate, 2 is the y coordinate, and 3 is the z coordinate. And let's look at what actually graphing a point is going to look like. So we're going to graph the point 1, -2, 3. So 1 is the x value, -2 is the y value, 3 is the z value. So if we take our flat edge out for at least some construction here, we're going to count 2 backwards in the y direction, which will give us a line coming out of there. And we'll go 1 in the x direction. I got fat fingered the ruler there. And then we can get our x and y points as they come together in the xy plane. And then we can go straight up from there. So turn our flat edge at a 90-degree angle and draw a line that goes up. And then if we kind of trace up 1, 2, 3 along the z-axis and go that same distance along this line that we've just drawn, hopefully we can end up with a point about right here, our point P. So it is 1 in the out direction, 2 in the left direction, and then 3 in the up direction. Right, and graphing and projecting a point. So we're going to define this new idea of projecting, where we can take a point and project it into another plane. So imagine we're just shining a light that is going to cast a shadow of our point P into the XY plane. So if we shine the light straight down, we could project it and give a projection into the XY plane. And we're going to look at projecting P into each of the 3 coordinate planes. So starting with projecting it into the XY plane, we're going to call that Q. So I'm going to take that point P and project it straight, point P, which is 2, 4, 3, labeled in the figure. Projecting it straight down, I should get to this point in magenta in the XY plane. That's our point Q. Then we'll do the same thing, but projecting into the XZ plane. We'll call it R. So for projecting it into the XZ plane, I'm going to project it directly to the left and get a point about there. You can sort of see the guidelines that I've already drawn out. So I have this box in the first octant, since my point is in the first octant. And finally, we haven't used purple yet, so we're going to project into the YZ plane, and we'll call that point S. And that should be this point over here. That's S. Forgot to say that this one is R. Cool, so there's Q, S, and R. And then we want to write down the coordinates for each of these points. So starting with Q, I've projected into the XY plane, which means that X and Y still retain their values, but the Z value is 0, because I've projected into the XY plane where Z is equal to 0. If I do that same thing for R, I've projected this thing into the XZ plane, which means that the X and Z values stay the same, but the Y value is 0, because we've projected into the XZ plane where Y is 0. So that's 2, 0, 3. And finally with S, I'm projecting into the YZ plane. So Y and Z retain their values, but X is 0. So that's 0, 4, 3. And again, we'll call those projections into another plane. So on a projection into the, for example, if I'm projecting into the XY plane, then the projection basically forgets the Z value, because we're taking something that was in 3 space and projecting it back into a plane. Okay, and one of the last things we'll say is a definition. The Cartesian product of a real number crossed with a real number crossed with a real number gives us the triple point XYZ. for x, y, and z all being real numbers. So x, y, and z are all contained in the real number set. This is a set of real numbers that we're going to call the 3D rectangular coordinate system, three-dimensional rectangular coordinate system. So, I mean, it's basically just saying, you know, we had our old x and y plane, and now we've added a third coordinate, z, to it. I'll finish this up with just a talk about what some equations are going to look like in 3 space. So if we take with our first example, the equation z equals 3, that means that our z value is fixed at 3, but both our x and y values are free to be whatever they want. So that's going to create a plane in 3 space. And it's the plane where z is equal to 3, so it's going to run parallel to the xy plane. Compare that to the next example where we've got y equals 5. Traditionally, y equals 5 would have been a line back in 2D space, so in just a plane. We have y equals 5, it's a horizontal line. But in 3 space, y equals 5 is a plane instead of just a line. Because if I only say that y equals 5, that means that both x and z could be whatever they want to be. So they could be anywhere, meaning that I have 2 free variables. If I have 2 free variables, that's going to create a plane. Rather, if, as opposed to in 2 space or a plane, when I have y equals 5, then it's just x can be whatever it wants to be. So I've only got 1 free variable, so only 1 dimension to worry about, which creates just a line. Let's also look at some circular shapes, and we'll compare x squared plus y squared equals 1 and the equation z equals 3 to just the equation x squared plus y squared equals 1. Back in a plane, if all we had was x squared plus y squared equals 1, so just in 2 space, that gave us a circle. But now that we're in 3 space, if we just say x squared plus y squared equals 1, we're going to get a cylinder, as shown in the figure on the right. Since we said nothing about z, that means z is a free variable. It can do whatever it wants. So we get a cylinder where we can move up and down along that z-axis as long as we stay within the circle x squared plus y squared equals 1. If we want to draw a circle in 3 space, then we'll also have to specify what plane we should be in. Check that out over in figure 8 on the left. We have x squared plus y squared equals 1, or the circle of radius 1, and z equals 3, so we're going to be in the plane z equals 3, which would have been the one that we saw just above in figure 7. So difference between a circle and a cylinder in the 3 space is just whether or not we've defined that third variable. We'll also take a look at figure 10, where if we have the equation y equals x, used to be a line and a plane when we were in 2 space. In 3 space, that's now also a plane. Just note that the way this is drawn is a little bit not quite the usual way. We've rotated the axes a little bit so we can kind of better see where this plane is going. And also, it appears as though we're just sketching out the part of the plane where all 3 variables are positive. But this plane would also continue going out in that direction, down in this direction, and then of course, we'd have some shapes that are down here in this octant as well. But the plane, could still keep going. We've just drawn, since a plane is going to continue on it'll continue on in 2 directions indefinitely. It's sort of hard to sketch an entire plane because, well, it's infinite. All right, and then wrap things up with a couple of definitions. This is really just expanding on some ideas that we already have from algebra. So we had a distance formula, which was basically the Pythagorean theorem, just sort of retrofitted to work with points instead of just side lengths. And we're going to use basically that same formula in 3 space to calculate distance as well. But in addition to the square root of x squared plus y squared, we'll also have a plus z squared term that goes into the distance formula. And then we'll also retrofit the equation of a circle to get the equation of a sphere. in much the same way that we retrofitted that distance formula. So the equation of a sphere is going to look something like x squared plus y squared plus z squared equals the radius squared. But if I go within each of that x, y, and z term and just subtract some constant number, I can move the center around. So if I have x minus h squared, that'll put the x coordinate of the center at h. So in particular, if we use the origin as the center, then we do just get the equation x squared plus y squared plus z squared equals the radius squared. So we look over at figure 12. There we have a sphere floating at some center, HKL, with a radius of r, sphere being just a three-dimensional circle. And let's look at one more idea of taking some circles and seeing what would happen. So if we fix x squared plus y squared plus z squared to be greater than or equal to 1, but less than or equal to 4, that means we're going to be in between a circle of, or a sphere of radius 1 and a sphere of radius 2. So don't forget to take the square root of 4 to get 2. So we're in between those two spheres. And we also have the equation that z is less than or equal to 0. So we're just going to take the bottom half of those two spheres, giving us the figure we see in figure 13.